Welcome to the Explainer. Today, we're going to crack open the Digital Architect's Toolkit. We're talking about the fundamental building blocks and really the recipes that engineers use to build literally everything, from your social media feed to the navigation app in your car. Have you ever stopped to wonder what's really going on under the hood? It's definitely not magic. It's architecture. There's this hidden world of organization and logic that makes everything, from your streaming service to your banking app, even possible. And today, we're going to pull back the curtain on all of it. All right, so think about it this way. Any great structure, it starts with the right materials. Well, in the world of software, those materials are called data structures. They're just the different ways we can store and organize information to get a specific job done right. Okay, let's dive into our first and honestly most basic building block, the array. The best way to picture it is like a long shelf with numbered boxes. Your phone's contact list? That's a perfect example. Every contact has a spot, and the app can jump straight to contact number 57 without looking at any of the others. It's incredibly fast for getting to something as long as you know its number. Next up, we've got the linked list. So instead of a fixed shelf, I want you to imagine a train. Each piece of data is like a train car, and it just points to the next one in the sequence. And here's the really clever part. What if you need to add a new car right in the middle? No big deal. You just unhook and rehook the connections. It's way more flexible than trying to shove a new box onto the middle of an already full shelf. Now for a structure that is perfect for anything with a natural hierarchy, the tree. And you use these all the time. Just think about the folders on your computer. You've got one main folder that contains other folders, and each of those contains more files and folders. See? That's a tree structure with everything branching out from a single root. And believe me, this toolkit is vast. You've got stacks, which work kind of like the undo button in a text editor, right? The last thing you did is the first thing undone. Then there are queues, which are like a line for a printer. The first document you send is the first one that prints. Hashes give you a nearly instant way to look up information. And graphs? Well, graphs are perfect for modeling networks, like mapping out all the connections between your friends on social media. So, we have all these materials. But materials alone don't build a skyscraper, right? You need a blueprint. In the digital world, our blueprints are called algorithms. These are the instructions for how we actually use our data structures to solve a real problem. Now, that definition sounds pretty complex, I know, but it's really just a recipe. Seriously, it's a step-by-step guide that takes some input, like an unsorted list of names, and produces an output, like that same list all sorted alphabetically. From recommending a movie to giving you driving directions, it is all powered by these recipes. And just like real architects have different design philosophies, algorithm designers have their own core strategies. The divide and conquer approach, it breaks a massive problem down into tiny, easy-to-solve pieces. A greedy approach makes the best possible choice at every single step, just hoping for a great overall outcome. And dynamic programming is the really efficient one. It's smart enough to remember the answers to problems it's already solved, so it never has to do the same work twice. Now, this is absolutely critical. You can have two different blueprints that build the exact same thing, but one might be 10 times faster or use 100 times less memory. So how do digital architects actually measure which blueprint is better? This slide is a perfect example of why this matters so much. Imagine you're looking for Smith in a massive old-school phone book. A linear search means you start at A and read every single name. Ugh. But with a binary search, you open right to the middle, say the M section. You know Smith comes later, so you've just eliminated half the entire book in one step. You do that a few more times, and bam, you've found it. The difference in efficiency isn't just a little improvement, it is absolutely transformative. And this brings us to the crucial idea of time and space complexity. It's the formal language computer scientists use for this whole thing. And it's not about using a stopwatch. It's about mathematically describing how an algorithm's performance, well, how it scales, as the problem gets bigger and bigger. In our phone book example, this is what tells us that one method barely gets slower with 1 million names, while the other just grinds to a complete halt. This whole idea of efficiency leads us to the very edge of what's possible with computers. Turns out, there's a class of problems so ridiculously hard that even with our best algorithms and our fastest supercomputers, finding a perfect solution could take longer than the age of the universe. This is the great divide between what are called P problems and NP problems. P problems are the ones we can solve quickly, like sorting a list. NP problems are different. We might not be able to find an answer quickly, but, and this is key, if someone just hands us a possible solution, we can check if it's correct really, really fast. Finding the single shortest route for a delivery truck visiting 100 cities is a classic NP problem. It's incredibly hard to solve, but it's super easy to check if a route someone gives you is valid. And that, right there, leads to this monumental question. Are those super hard NP problems truly hard? Or are we just not smart enough yet to figure out a fast recipe for them? If it turns out that P does equal NP, well, it would revolutionize everything. We're talking medicine, logistics, finance, AI, you name it. So with these grand challenges looming ahead of us, what's next? I mean, where do we go from here? The field is constantly evolving, developing brand new architectural tools to tackle what seems impossible today. To tackle these massive challenges, we're designing whole new kinds of tools. Parallel algorithms basically unleash thousands of computers on a single task all at once. Randomized algorithms, they use a bit of pure chance, like flipping a coin, to find surprisingly good answers fast. And when a perfect answer is just way too slow to find, approximation algorithms can get us a solution that's maybe 99% perfect, but in a tiny fraction of the time. So there you have it. From the simplest app to the most complex scientific simulation, literally everything is built from this fundamental toolkit of materials and blueprints. It's the invisible, elegant architecture of our modern age. And knowing these tools exist and seeing the frontiers we are pushing right now, it leaves us with one pretty exciting final question. What will we, the digital architects of the future, decide to build next?